It's okay. I think it's all right.
All right, well, it's good somebody has sharp eyes. That's too bad that
I'm sorry.
a good fraction of the lecture is gone, and there are some students who didn't come. Okay. Maybe you two should switch places.
Well, I think it's recording now, so it's
You think
fine.
so?
Yeah.
Okay. Now, this is a very suggestive expression. These things are projection operators. You can think of this as a Hermitian operator. And this, you can then think of an experiment in which you have some beam of particles, and you were then measuring some property of the particles in this beam, and that is separating them into different states. And so they all come along, and then you separate them into ones with spin up or spin down, or if it's something that has a lot of angular momentum, you might have spin up -1, up -2, all the way down. And this is thought of as you can think of this as a representation of a selective non-destructive measurement. Anyway, Schwinger wrote some articles about that there. I think they're published in the Proceedings of the National Academy of Sciences, probably sometime in the 50s, a long time ago. Okay, now, in this basis, the matrix, of course, the linear operators, the matrix representing the linear operator is diagonal, and we call it AKJ, which would be, let us say, KAJ would be A sub j delta kj. On the other hand, if you take the linear operator in any other basis, maybe I should call it alpha A, so I'm writing the thing a little bit differently. We call this A alpha beta, and this would be then a sum on K, alpha K, A sub K, K beta, and we could call this a unitary operator U. Alpha K would be then alpha K, and U dagger K beta would be K beta, and this would be U beta K complex conjugate, and consequently U beta K would be K beta complex conjugate, which would be beta K. So this is then writing this A alpha beta would be U alpha K A sorry, this is diagonal, so this would be this would be the diagonal matrix K. Well, it would be the KK element, and then this would be U dagger K beta. And so that's writing it in diagonal form. This is the diagonalization of the matrix, and this would be K equals 1 to n. Okay, so basically an arbitrary n by n Hermitian matrix has n real eigenvalues. It has n orthonormal eigenvectors. You can write it in diagonal form like this. In general, it's the matrix is a unitary matrix. It's diagonal form U dagger, and so you write this as A diagonal U dagger, and then multiplying by U dagger, you get U dagger AU is equal to A diagonal. So those are the various ways of thinking about it. Okay, I'm going to skip the examples because we only have a little bit of time, and pass now to a generalization of Hermitian matrices, which are called normal matrices. Now, these normal matrices are like Hermitian matrices, and in fact, it's very simple to say what a normal matrix is. A normal matrix, I'm going to still use A for the symbol, but for the moment, let's use N. This would be U, N diagonal, U dagger, and this would be a diagonal matrix, but instead of having real eigenvalues, it has arbitrary complex eigenvalues. And so this gives you then a general normal matrix. And normal matrices have a very simple property, namely, if you take the adjoint of the normal matrix, what you get is U ND complex conjugate U dagger, and consequently a normal matrix commutes with itself, because this would be the commutator of U N diagonal U dagger with U N diagonal complex conjugate U dagger. And now you see the U dagger U's are just the identity when they touch each other, and so this is actually U N diagonal complex conjugate U dagger. Any two diagonal matrices commute, and so this is 0. So there's an obvious generalization of a Hermitian matrix or a Hermitian operator, which is you just relax the reality condition on the eigenvalues, and you get what's called a normal matrix. And so normal matrices commute with their adjoints. That's the definition of a normal matrix. And okay, well, we can do a little more, though. We can now show that if a matrix commutes with its adjoint, then it has n orthonormal eigenvectors, but the eigenvalues are just complex. We can't say that they're real because they need not be real. So what we're going to start with then is write down the eigenvector equation. I'm writing the normal matrix as V. So this is let's put it this way. V is an n by n matrix, an n by n normal matrix. Consequently, it has n eigenvectors with n eigenvalues, and as yet we don't know whether these eigenvectors are orthonormal or linearly independent. But the square of the norm of this vector is k v minus vk, this is a v, times the identity adjoint times v minus vk times the identity k. On the other hand, it commutes. If we bring the adjoint through, we get a dagger there, and the adjoint of the identity is obviously just the identity the matrix is normal, so it commutes with its adjoint, so we can set it equal to V minus eigenvalue, identity, V dagger minus V, complex conjugate. I forgot complex conjugate. I, K, and this is equal to 0 because it's K is an eigenvector of the normal matrix V. Okay, so what does this say? This says that VK, that this vector has 0 norm. And that means that V dagger on K is equal to VK complex conjugate K. That's because the norm of that vector vanishes. And if we take the adjoint of this equation, what we have is K V is VK. Okay, now we play the same game as we had before with Hermitian operators. Suppose M is another eigenvector of the normal matrix V with eigenvalue Vm. So then we can form this bracket and letting the V act on M, you get V sub M Km. Letting the V act on K, we get Vk. So this is Vk Km. And now what we have is Vk minus Vm times Km equals 0. So what we see is if you have a normal matrix, the eigenvectors are, this thing is 0 if Vk is not equal to Vm. So this is very similar to what we have with Hermitian matrices, namely that if the eigenvalues are different, the eigenvectors have to be orthogonal. On the other hand, what we can do now is play the same mathematical trick as we did with Hermitian matrices. Namely, we can say, suppose Vk is Vk K. Suppose Y is a vector that's orthogonal to an eigenvector. Then the vector AY is also orthogonal to K. Oh, sorry, I switched to A. This is V. But KV is VK, so this is VK KY. So if this vanishes, this is 0. So in other words, if you have any vector that's orthogonal to an eigenvector of a normal matrix, the image of that vector under the normal matrix or normal linear operator is also orthogonal to the eigenvector. So it's exactly the same as for the Hermitian operators, and consequently going through that same argument, which I'll mercifully not repeat, we see that every normal, well, I mean, this is illimitable. Every normal n by n matrix V has n orthonormal eigenvectors. N orthogonal eigenvectors, you can always normalize them. So n orthonormal eigenvectors. Okay. So, in other words, the intuition from over here is totally valid. So normal matrices are a special, Hermitian matrices are a special kind of normal matrix. They're the normal matrices with real eigenvalues. Normal matrices aren't used as much in physics, but who knows, maybe they will be in the future. Okay. And if you have then a normal matrix, and you have a function of some normal matrix, well, what you can do is diagonalize it. You can write it as U f of n diagonal, U dagger, and so this is a diagonal matrix of where you have the first eigenvalue, the f evaluated at the first eigenvalue, f evaluated at the second eigenvalue, f on the nth eigenvalue. I'm sorry about using one n for a subscript and one n as a label. That was a little bit silly, but I trust you know what I meant. Okay, compatible normal matrices. Let's just say a few words about these. Two normal matrices, A and B, that commute are said to be compatible. Now typically in physics classes we're talking about a special kind of normal matrix, namely the Hermitian matrix. But we could just as well talk about normal ones. Since they're normal, they both have complete sets of orthonormal eigenvectors. And if, let us say, A on U is equal to ZU, then A on BU, since they commute, it's B on AU. This is Z, B on U. So this says that if U is an eigenvector of a normal operator A, and B commutes with A, then BU is an eigenvector of the same operator A with the same eigenvalue. And in quantum classes, this is used a lot. But of course, for the case of Hermitian matrices, we don't normally use it for normal matrices. Anyway, we can write this then, since it is diagonal, we can write it as AK. So I'm just writing the eigenvector of the normal matrices as I'm labeling it by its eigenvalue. And so we know that they're compatible. So what we have is A sub L, AB minus BA, A sub K. This would be A sub L minus A sub K times A sub L B A sub K. Okay, well that tells you then that if the eigenvalues AL and AK are different, then the eigenvectors, then the matrix B, or the operator B, is diagonal with respect to, in terms of these, or let's say all the eigenvalues were different, to make it simple. Suppose all the eigenvalues of the operator A are different, then these would all be non-zero, and B would be diagonal. Now that's only true if the eigenvalues or the eigenvectors are non-degenerate, of A are non-degenerate, but continuing with that, this operator B, again, where the eigenvalues of A are non-degenerate, then B can be written as a sum A sub L B on a sum on K, A sub K, and this then would be diagonal, and so this would simply be a sum on L, A sub L B, A sub L. So B is then diagonal on that basis, and moreover, B on AK would be this sum, AL, B, AL, AK. This is delta LK, and so this gives you AK, B, AK, state K. So in this case, where the eigenvalues of A are non-degenerate, B, which commutes with A, maps any of its eigenvectors, this is an A sub K, maps any of the eigenvectors of A into other eigenvectors with these eigenvalues. So these are the eigenvalues of B. So the eigenvalues of B are then the diagonal matrix elements of B in the eigenvector basis of A. Okay, well, in general, of course, the eigenvalues of A are not going to be all different because there'll be some symmetry. And what happens then is that you have some of the eigenvalues of A are different, and then you have you have some of them that are the same. For those ones that are the same, in that basis, B won't be diagonal. On the other hand, you can take linear combinations of the eigenvectors of A in such a way as to make this block diagonal. All right. Anyway, I think that's enough about that because there's some other stuff that I want to get to, which is more important. You can read some of the details in the book. The next topic is the singular value decomposition. And I was once at a conference in Santa Fe on biophysics, actually. And biophysicists just love MATLAB, and they also love Steve Moeller. Steve Moeller was there, and I told him that I had written a book on mathematics that physicists use, and in particular linear algebra. So he said to me, "Did you do this singular value decomposition?" And I did. And I said, "Yes." And so he was surprised because in physics departments it's very rarely mentioned. So let me tell you what it is. It's in any matrix A. So now we're not saying anything about it. It's just complex. It's not even square. In fact, it's m by n. It can be written as U sigma V dagger. This U is unitary and it's m by m. This is the singular values, and this is diagonal. And real and non-negative. In other words, sigma is in general a rectangular matrix, but on its main diagonal, which of course if the matrix isn't square, it runs it doesn't hit the opposite corner, it runs into one of the runs into the side, or it runs into the bottom, into its bottom. But on that main diagonal, the numbers are real and either positive or zero, and all the off-diagonal elements of sigma are zero. And this is n by n and unitary. So U and V are both unitary. Okay. Yeah.
So would sigma then have to be n by n?
Yes. Did I write n by n?
Well,
No. Sigma is
m by n, right? If you have one.
Sigma is m by n.
M by
It's
n.
rectangular in general.
So how can you have what is a diagonal rectangular
Well,
matrix?
All right. Suppose it might look like this: 3, 2, 0, 0, 0, 0, 0, 0.
Okay.
Or it might look like 3, 0, 0, 2, 0, 0.
Okay.
So it's on the main diagonal, the elements are positive or zero, and all the other elements are zero.
Okay.
Okay, now, how do we think about this? Well, A is a linear operator that takes you from an n-dimensional vector space into an m-dimensional vector space. And, of course, in each of these vector spaces, there are many different bases that we could choose to represent the identity operator. We could write I sub n as a sum aj, and this would be j equals 1 to n. And we could write I sub m for this space as a sum, what did I call it? K equals 1 to m, bk, bk. Okay. And any of these bases, let us write the operator A as it would be a sum on K, a sum on J, and it would be BK, BK, A, AJ, AJ. So this is, so you have just, infinitely many choices of basis for the n-dimensional space, say Sn, and the m-dimensional space Sm. And the singular value decomposition then is a choice of basis, and in effect, it's the choice of basis in the space that on which A acts. Okay. Now, actually, it's very simple. So it's a choice of special basis, and what is the choice of special basis? The special basis is such that BK A, AJ is some number Sj delta Kj. And of course, in that case, we can write A as a sum on J, Bj, Sj, Aj. All right. Now, what is this special basis? What are the special kets that you choose as your basis vectors in the space S sub n? Well, it's very simple. They're the eigenvectors of the Hermitian operator A dagger A. So notice A is m by n, A dagger is n by m, so this is a perfectly sensible matrix multiplication. Moreover, it's a Hermitian matrix, not only Hermitian, but it's non-negative. It can't have any eigenvalues that are negative. So this is equal to Ej, Aj, and these Aj's are n, and we can choose them to be orthonormal because they're the eigenvectors of a Hermitian operator. Okay, Ej is the squared length of a certain vector and is positive. In other words, it's Aj, A dagger A, Aj, well this is Ej, Aj, Aj. We choose the length of Aj to be 1, and so this is Ej. So Ej is obviously greater than or equal to 0. What are the Bj's? Well, the Bj's are kind of obvious because the Bj's are just, from the point of view of a vector, they're what A maps Aj into. In other words, this form says that when A acts on Aj, maps it into Sj times Bj, and so we divide by Sj. Okay, so this is the formula that we use to define the kets in the space S sub m for the case in which Sj is non-zero. Now, if Sj is 0, well, what does that mean? That means that A maps Aj into 0. So, in effect, we don't really care about this thing because in this decomposition, the singular value decomposition, we have a 0 here. So we don't really need to know what these are. For practical purposes, what one does is one finds, for the case where the Sj's are non-zero, or where they're positive actually, one has the Bj's. They are orthonormal to each other, they are orthonormal, and then one picks any old vectors that are orthonormal and perpendicular to these vectors to complete the set. So one could add those vectors to the J there, but they're multiplied by 0, so they don't really matter. Okay? All right. Let's take the inner product of these things. Bk with Bj is 1 over Sk Sj Ak A dagger A Aj. This is then Ej over Sk Sj times Ak Aj. This is delta. So this is Ej delta Kj over Sk Sj, and so this is simply delta Kj because did I define what? Did I say what the? I must have skipped that. Yeah, I forgot to say that Sj is the square root of Ej. So when the Ej's vanish, the Sj's are 0. That's why this thing cancels. Okay, so that's the singular value decomposition. And once again, if you, just to see how it works, you write A as A acting on the identity operator for the space Sn, so that it's A on J, Aj, Aj. This is the sum, of course, A on Aj, Aj. And then this is Bj, Sj, AJ. So that's the singular value decomposition. How many J's can there be that are positive? Well, at most, the minimum of M and N. So this sum is up to the minimum of M and N. And it goes from K equals 1 up to the minimum of M and N. Okay, so that's the singular value decomposition. You might say, well, tell me a little more about the BJs. Okay, if you want to know more about the BJs, I'll tell you a little more. Consider the operator a dagger. This is an n by n matrix. Do I have that right? No, m by m matrix, and it has m eigenvectors, and these in fact are the eigenvectors Bj. In order to see that, we just write this. We could see it independently, but in order to see it simply, let's just use the singular value decomposition for A. So that's the sum on J, Bj, Aj, Sj, and now sum on K, Sk complex conjugate. Well, they're all real, so we don't need to complex conjugate them. This would be then AK, BK. And now these guys are orthonormal, and so this is a sum on J, Bj, Sj squared, Bj. And so now we see that the Bj's are simply the eigenvectors, the orthonormal eigenvectors of the Hermitian operator AA dagger. Now, MATLAB is marvelous for doing matrices, and let me just tell you how one would, well, look at the examples in the book, but basically it's super simple. You just basically, if you define some matrix X, you just say U SV equals SVD of X, and hit return, and bingo, MATLAB will give you the unitary matrix U, the non-negative rectangular matrix S, and the unitary matrix V. And that will all be such that X is equal to U, S, V dagger. All right, so that's the singular value decomposition. It turns out that the singular value decomposition allows one to define what's called the Moore-Penrose pseudo-inverse. And so suppose you have a rectangular matrix, and you know, well, a rectangular matrix is not going to have an inverse unless it's square, but you might say, well, I want something that is as close to being the inverse as possible. And so that is what's called the Moore-Penrose inverse, and it's written as A+. And it is simply V sigma plus U dagger. So in other words, if A has a singular value decomposition U sigma V dagger, then the pseudo-inverse is V sigma plus U dagger. Now I have to tell you what sigma plus is. Sigma plus is, first of all, the transpose, or the adjoint of sigma, But the non-zero values, you take the inverse of the non-singular values. So sigma plus it's basically sigma plus is effectively sigma transpose, but inverse in the sense that you invert the non-zero elements. So suppose sigma is equal to, in fact, let's go over here where we have some sigmas. Can you turn the camera? Suppose this is sigma. Okay. Sigma plus then would be 1/3 0 0 1/2 0 0 0 0. So if this is sigma, that's sigma plus. If this is sigma, then sigma plus is 1/3 0 0 1/2 0 0 0 0. So that's sigma plus. So this is, as I said, the Moore-Penrose pseudo-inverse, and back when we did linear least squares, and I gave you Gauss's, I think it was Gauss's solution for the best estimate. It turns out that that the expression is the Moore-Penrose pseudo-inverse. That's what was used. So in other words, if you have an equation, ax equals y, what you write is x is Moore-Penrose pseudo-inverse y. So that's basically the utility of this. I don't know who Moore is. Penrose is or was an English relativist. He was mainly working on general relativity and possibly quantum gravity. All right, let's see. Is there anything else that I can fit in 1 minute? Okay, the rank of a matrix. This is a term that's often used, and it's just a definition. Many definitions. The rank is the number of linearly independent rows. It's also the number of linearly independent columns. It's also the number of non-zero singular values. And it's the number of rows or columns in the biggest square non-singular submatrix. These are all equivalent. This is all in the book. All right, the next topic we don't have time to do today, but I think I can easily. It's 5 minutes that we can do Tuesday. You should go to the colloquium tomorrow. It's, if I'm not mistaken, it's by Wineland, who's a Nobel laureate in some form of optics. I don't remember if he does theory or experiment. I expect experiment. So that should be something to go to. So you should show up at room 125 Dane Smith Hall at around 3:15, and so you should, as I say, you should go to all the colloquia, but the reason I make the homework due at 3 o'clock on Friday is because I don't want you to skip the colloquium in order to finish the homework. All right, well, why don't you turn it off? I think it's by pressing the same button.